Right, we'll use this one then. Welcome. Welcome everybody to this AGM, British Astronomical Association. Welcome to anybody who's joining us on the YouTube live stream. They can join from all over the world. And I'll try and have a look at that live stream later and see if there are any questions from anybody on the live stream. But any member here can ask any questions of myself or the other officers. That's what the AGM is for. This is the final meeting of the 134th year of the BAA, and we're now starting on the 135th. So first of all, is Bill Tarver here?
Yes.
Right. I would like Bill Tarver to, he needs you to approve the minutes of the 2023 AGM. Well, I can ask them to approve them actually.
Please do.
Yeah, you have been sent, oh, well, you haven't actually been sent them. They've been on the website.
Get on the website.
The minutes of the last AGM have been available. If anybody has read them and has got any comments on them or corrections to them, please let me know. Right, I will certify those as passed, the minutes of the 2023 AGM. Thank you very much, Bill, for writing them. Bill writes all our minutes for our council meetings, board meetings, and AGM. He does a fantastic job. Next, the Treasurer, Graham Winstanley, will give you his view on the association's finances. You've had the full figures published in the journal. He's going to present a summary, and you may ask any questions. So, Graham. Gives a bit of an echoey effect, this.
Okay, thank you. Good evening. I'm just going to quickly run down the figures. I don't know how carefully you've studied these in the journal. We had a bit of an increase in our income during the year. Largely the increase in donations. We had a legacy came in for about £20,000. And another generous donation of 5,000. Advance? No, is it down?
Sorry.
That one. Okay, thank you. Then likewise, we've got a similar sort of increase in total expenditure. So that leaves us with a deficit at the bottom here of 72,000, which is considerably less than we had the previous year. One of the main reasons, though, is that there was some expenditure that didn't come in within the year, and it will probably be hitting us in the current year's accounts. Right, but our guardian angel is our investments, and our angel came very good this year and gave us a considerable increase, as you can see there, of something like £172,000. Compared to the previous year, when our investments actually went down. So that year was a reminder that our investments can go down as well as going up. Fortunately, historically, they have tended to go up rather more than go down. Right, and then just to show the effect it has on our total reserves. So we have an increase of something like £100,000 over the 12 months. So the investments have more than covered the deficit that we're running each year. The deficit on our activities is planned, and in fact we had planned for a similar figure to the prior year. As I say, some of the items will fall in the current year. Just to highlight one or two items from the more detail in the accounts. Subscription income has increased slightly, fairly steady. Of course, this is our main source of income each year. Then some items of expenditure, document collection and archives. There is some expenditure there that has come through into the current year, where we had budgeted for it to be in the last financial year. So that's why that's down. Likewise with legal fees, there's been an ongoing case over a disputed legacy. That should be finalised by the end of next month, hopefully. It should have been the court case in October the previous year, but it got delayed. And accountancy fees. Now, we were paying £7,000 for the annual accounts work. In the preceding year, there was this extra £1,900, which was for a different exercise by the accountants. But we've changed accountants for auditing the accounts last year. Sorry, not auditing, it's independent examination. And instead of 7,000, we've managed to get that down to £4,000. So having saved 3,000 over the year. So that's my main comments, and financially we're still in a very healthy position. So I'm happy to try and answer any questions.
Over the last few years, because we've been looking at reducing office costs, etc., moving out of Burlington House, has that really reflected in a greater saving as expected? Or?
Well, certainly the premises costs are very much less than they used to be, and enormously less than what they probably would be if we were still in the same offices. Because we don't actually have a permanent office anymore, because the office staff are working from their own homes.
Okay.
Yes, we haven't saved all that money because there have been extra expenditure as a consequence of that. For instance, relocating the archives and hiring the space for them. But then we wanted to do that because the place where they've been relocated to is a place where they can be scanned, and we wanted to do that, and we wanted to make them available to members on the website. So that's led to a new service that we're offering. So I would say there have been costs that are consequent on moving out of Burlington House, so we haven't simply saved all the rent that we were paying to them. And David at the back. Adam. Well, sorry.
Yeah, given that we're in a good, healthy financial situation, which I would agree, and I think we should be a going concern for many more years. When we get donations and legacies, do we just stick it in the bank, or are we going to spend them on something that we wouldn't normally have or buy? Yeah, I mean, is there a plan to spend?
At the moment, they have just gone into the bank.
Yeah, occasionally we do get specific requests. People want money spent for particular purposes, and then, although we don't put it in a special account, we do discuss that at the council and try and meet, obviously, the wishes of the donor. But most donations, no, they're not linked to any specific requests. But your point about that we should be spending money that we get on doing our job, which is creating services for the members and also popularising astronomy, yeah, that is very much in our mind all the time.
It might encourage more donations if they knew it was going to be spent on something additional to our normal ongoing costs.
true.
Right, I think there was another question.
Question over here.
Could I ask what was the underlying value of the investments on which you've earned the £172,000 this year, approximately?
Approximately 1.5 million.
Oh, okay, great. That's a very good return. And supplementary then, would you mind managing my pension for me?
I am not an investment manager.
Boy,
The
that's
money is
excellent.
actually managed by CCLA.
That's an, well, that's an
And
excellent.
it's in a
that's an
charitable
excellent number.
fund.
It's a fund that's only available to charities.
That's right.
Yeah.
But if you want to make yourself a registered charity, you can take that.
Well, I probably would qualify. Thank you.
Right. Thank you very much, Graham, for that summary of the situation with the finances. Now move on to the President's Review of the Year. That's my review and last review of the year. I only have time to give a very brief account of the last year. There's more detail in the report of the Council, which has been published in the journal. As usual, I'll mention deaths first of all. We had, in the year to 1st of August, 27 deaths of members, most notably that of Roger Pickard. Roger Pickard was president from 2007 to 2009. He was the longest ever serving director of the variable star section for 20 years. He brought very many people into astronomy and variable star observing in particular through his quiet enthusiasm and kindness and generosity with his knowledge. He was a very faithful servant of the association. I'll also remember Professor Brian Warner, who few of you will know. He had not been involved with the BAA in recent years. He died after 68 years of membership. He was director of the lunar section for 2 years in the 1960s. He then became a professional astronomer, moved to America, and had a long and very successful career as a professional astrophysicist specializing in cataclysmic variable stars. So we'll now hold a brief silence in memory of Roger Pickard and Professor Brian Warner. Thank you very much. Now, much more happily, Hazel Collett, our former meeting secretary and still the organizer of these meetings at the IOP, she has been awarded the British Empire Medal to recognize her contribution to astronomy and the BAA and to her local society in York. She was meeting secretary of the BAA for 18 years, and she received her medal in September there from the Lord Lieutenant of North Yorkshire. And there is the medal. And as you can see, Hazel dressed up very well for the occasion, so she was delighted with that. Now, going back to the 2023 AGM, there she is again. I presented her with some presents on behalf of the BAA to mark her retirement as meeting secretary. And at that meeting, we also had a live link from Namibia with the Stevenson Award winner, Clyde Foster, and there he is showing his certificate for the Stevenson Award. And on that occasion, I gave the second part of my presidential address about the history of the telescope. And we'll have more about telescopes later. Then at the Christmas meeting last year, I presented the Goodacre Medal to Nick James, and the Stevenson Award to Paul Abel, the Horace Dall Medal to Stephen Floodgate and Dave Grist, and the Sir Patrick Moore Prize to James Dawson, and the Cicely Botley Prize for contributions to our publications to Anne Davies. She's there on the left receiving her certificate. And there was also a Cicely Botley Prize to Alan Dowdall. We had a talk on that occasion as well from two Glasgow astronomers, Professor Martin Hendry on gravitational waves, and from Professor Lindsay Fletcher on the solar atmosphere. And last Christmas, the IOP allowed us to hold a drinks party after the meeting, just outside here, and you were all reasonably well behaved, actually. So, surprisingly enough, they've agreed to do it again this year. So we will have a drinks party after the Christmas meeting this year, and there's a booking form on the website. You have to book for it, but there's no charge. So that's, we're being very generous to you. So sign up as soon as possible. Last January, I presented the Lydia Brown Medal and Gift. There's the Christmas social at the IOP. In January, I presented the Lydia Brown Medal and Gift for meritorious service to the association to Janice McLean. There she is, receiving her medal, and she can't be here today because before she knew that she had been nominated as president, she had booked a holiday. So she's away, but she will be here in December. She will be in charge of the meeting, the Christmas meeting. At that meeting, the January meeting, we also had a talk from Mike Frost about a book he's been involved with, Eclipse and Revelation. Although it doesn't mention him on the cover, it was one of the editors, Tom McLeish, died, and Mike Frost took over from that, and he produced that book, which he told us all about. And we also had a talk from Mary McIntyre on her adventures in outreach, which was quite entertaining. And the March meeting, we had talks from two of our section directors, Dr. Richard McKim on Mars and Dr. John Rogers on Jupiter. We had the Winchester weekend, which was very close to the American total solar eclipse in time, which meant that some of the regular attenders perhaps went there. But it was a great success. The program was arranged by Stuart Eaves with assistance from Tony Hirsch, and our stalwart Anne Davies remained very much involved. We had the Alfred Curtis Memorial Lecture from Professor Don Polacco on his digital telescope concept, and I chaired a meeting of the equipment and techniques section. And on the Sunday, I sang a song. We had a revival of the BAA song written by Professor Herbert Hall Turner in 1924. So we had a centenary revival of the BAA song. And we had more music as part of the spring one-day meeting. That's an important part of Winchester's, the food, which is always very good. And a bit of observing occurs there as well. So in May, we held a spring meeting, a whole day meeting in scenic Greenock in Scotland, and it really is scenic. That's the view from our meeting place across the Firth of Clyde. And Marion McNeill, who's in charge of Inverclyde Skywatchers, devised an ingenious program for us on the theme of the music of space. And we had a talk from Dame Jocelyn Bell Burnell, and we had an actual concert of choral music on space-related themes. And to top it all off, we had the most spectacular auroral display for 20 years. On the night of 10th to 11th of May, I don't know who organised that, but well done to them. That's a picture of it taken not from our meeting, but from slightly further north in Scotland by our member Alan Tuch in Elgin. So, and that was seen as far south as Italy. So you can imagine it was very spectacular as seen from Greenock, and I watched it from the banks of the Clyde in the middle of the town, and it was, you could see all the colours very clearly. So all that was very memorable. Moving on to the June council meeting, the council decided to award the Walter Goodacre Medal to Alex Pratt, the Merlin Medal to Jonathan Shanklin. Oh, there's Philip Jennings observing the sun outside the Beacon Centre in Greenock. Right, the Merlin Medal to Jonathan Shanklin, who's given great service to the BAA in the past as Comet Section Director. He's now stepped down from that. And the Stevenson Award was awarded to Richard Miles, Director of the Asteroids and Remote Planets Section. And we also voted to give a Lydia Brown Medal to Steve Harvey for his work on the handbook over many years. And we had the George Alcott Memorial Lecture on that occasion from Professor Bill Leatherbarrow about the craters of the moon. And we heard from Peter East about amateur detection of pulsars. The last meeting of the year, it's quite recently, in September, the autumn one-day meeting was held at the Rutherford Appleton Laboratory in Oxfordshire. That was organised by Anne Davies and David Boyd, and also members of the Newbury Astronomical Society. And that's Paul Gibson shaking hands with me, chair of the Newbury Astronomical Society. They did a great job. The meeting was themed around current research highlights, and we had leading professional researchers in astrophysics and planetary science talking to us. It was a very popular meeting. Facilities at the RAL were very good, the food was good, and we had a capacity audience of over 100. We've had various section meetings over the year, webinars, too many to mention really, solar, deep sky, historical, asteroids, equipment and techniques, radio astronomy, exoplanets. So thank you very much to all the section directors who've organised those. They very much add to the menu of activities that we offer to our members. Amongst our other services that we've been developing in recent years are the archive. We've got a huge historical archive of members' observations, and a large amount of this material has now been professionally scanned, and it's in a state-of-the-art archival online system. You can get access to this by application to the archivists, and we've got the records in there of very famous astronomers, Molesworth, Bertrand Peake, Thomas Elgar, Reggie Waterfield. There's one of the lunar notebooks of P.B. Molesworth from 1896. And we've even got the records of one person who's still alive, very happily. Alan Heath has donated his logbooks to us, which we're scanning. So that's been a big ongoing project, and it's great to have all that preserved, so it cannot be lost now, and it's available to the membership. The BAA Journal is our flagship publication, of course, and we took the decision to make it longer, to increase its scope, add some new features, and also the expansion was intended to reduce the backlog of reports and papers, so allow us to publish things in a more timely manner. The journal is produced by the editor, Philip Jennings, and his assistant editor, Indra Baines, who was just appointed at the end of the last session. And I think member feedback on the expanded journal has been positive. We have had a bit of a hiccup in that we were not able to issue the 2025 handbook with the October journal. This has been the result of several circumstances, which I won't go into, but I'm very grateful to Indra Baines, Philip Jennings, and a number of members of the council, especially Richard Miles, Nick James, Tim Parsons, for doing fantastic work over the last few months to pull this together and ensure that we should be able to send the handbook out with the December journal very soon. We took a decision to create a new section, the outreach, it's called the Education and Outreach section. This is a thing we don't do very often. We don't create many new sections. The objective is to harness the energy of those in the BAA who are interested in getting involved with education and outreach in astronomy. And we want to reach new groups of people who are not normally reached by the BAA. Of course, a lot of outreach we know is done by local societies, so we want the new section to work with local societies and with the SPA, with the Royal Astronomical Societies, and so forth. The director of the new section is Helen Usher, who you may have heard of through her Comet Chasers project, which gets school children doing scientifically useful observations using remote telescopes. So, wish the new succession success. This year, the House of Commons Science, Innovation and Technology Committee held an inquiry on UK astronomy, and I provided written evidence to that on behalf of the BAA. And this resulted in me being invited to give oral evidence to the committee in Westminster. So I spoke to the MPs, I explained what the BAA does, especially talked about its contributions to science and how amateur astronomers are a critical part of the whole astronomy scene. And I also made known to them our worries about light pollution and satellite proliferation. Hard for them to do anything about satellite proliferation, but light pollution is a more local problem, and I really try to emphasize that the government, which of course has changed since then, that the government should do more about light pollution. Administrative matters, there's me addressing the committee. We changed our accountants and our registered office address. So the accountants used to be RSM at Farringdon Road, London. The accountants are now Stevenson, Nuttall and Co. in Newark, Lincolnshire. This change has no effect on members. So you can continue to contact the BA office on the existing address and phone lines. We continue to employ one full-time employee and 2 part-time to run the BA office. We are still pursuing 2 ongoing legal cases, as has just been mentioned. The first one has not been mentioned. The first consists of continued action against the former curator of instruments, R.A. Marriott, in respect of items in the former BAA instrument collection. And there's been no developments in this case in the last year, owing to huge delays in the court system. The other case is that of the disputed will of our late member, Roy Panther, and that is getting close to settlement, I think I can tell you, hopefully. So more news on that soon. It's a complicated case. Now, we held a special general meeting in January to approve changes to the bylaws. There were some changes to our bylaws. We ended the practice of members voting annually for subscription rates at a special general meeting. In future, the subscription rates will be voted on only by the council. And we also gave the board the authority to not do a postal ballot, but to have an online ballot only for the Board of Trustees and Council, and we did that this year. And we offered the postal option as well, but nobody took it up. So it's going to be online in future only. And we changed the nature of society affiliation. We still will have affiliated societies, but we won't treat them as members in future, and we won't charge them a subscription, and they won't get the journal unless they subscribe to it specifically. But their members can still get the BAA members' rates for going to meetings where we do make charges for meetings, which of course we don't for the meetings here in the Institute of Physics, because we have a very good relationship with the Institute of Physics and we get a very good deal from them, I would say. The special general meeting, we also had a discussion on the slightly controversial issue of honorary membership. This was part of changes to the membership categories that were agreed by Council. These changes were brought into force in August, and we've now abolished senior membership, and the seniors pay ordinary membership rate. Yeah, that's the page about that. So senior membership has been merged with ordinary membership. We're not going to create any new family memberships, although the existing ones will continue. And we are not going to create new honorary memberships. Honorary membership was after 50 years of continuous paid membership of the BAA, you got free membership. So that will end in 2 years' time. And there was a discussion about that at the members' meeting in January, where most of the members agreed with the council decision. And there is a new category of benefactor membership as well, for those who wish to contribute more. That's your lovely council, or those members who are present at the June meeting. There are some changes in the council this year, or from today. Well, some of the trustees are leaving, they're retiring. Alan Lorraine, former president, Jeff King, former treasurer, and Richard McKim are leaving the board. So thanks to them for their service on the board over the 3 years of my presidency. From the council, Steve Harvey has resigned, Mary-Louise Archer and Peter Carson. Steve was director of the computing section, and Mary-Louise has been our advertising manager for the journal and also doing work on the Back to Basics meeting. And Peter Carson has been the new members coordinator. So thank you all very much for all their voluntary work to them. And I should also mention that John Mason retired from his post as the BAA's public relations officer, and he held that post for 30 years. Patrick Moore, when he was president, invited John Mason to be the BAA's public relations officer. So he retired from that, but John continues to serve as director of the media section. Membership at the end of September was 2,533. That was a reduction of 2.5% on the figure for the previous year. We've had a slow decline in membership in recent years, and I regret that during my tenure as president, I've not been able to reverse that. It's a cause of regret to me. It emphasizes the need, to me at least, for the association to evolve and to offer new activities, services. Having a great history is not enough. We must change to remain relevant to the modern world. And that is my departing message as president. We've held a ballot recently, and we now have the results of the ballot, and I will ask Bill Tarver to read them out as well.
Thank you. The ballot was managed wholly by Civica. There were no paper returns whatsoever. So thanks to Civica for taking it on and looking after it. Results. The President, Janice McLean, 393. David Arditti is now Vice President, ex officio. Graham Winstanley is a treasurer with 385. Bill Tarver, business secretary with 368. And Jeremy Shears, paper secretary with 389. Trustees, five elected to the trustees. Jeremy Shears, 300. Lynn Smith, 290. John Shooter, 283. Mike Frost, 281, Tim Parsons with 199. Steve Knight has stood as a trustee, and his votes are carried over to his position in council. And 5 elected council members: Bill Leatherbarrow, 321, Hazel Collett, 319, David Boyd, 316. Total votes for Steve Knight, 284, and James Latham, 264. And Steve Floodgate just missed out on 228. The online voting through Civica costs about $1,500 this year. So please, if you haven't voted online, it's very, very simple, and just use it. We pay for it. Okay, total votes cast, 435 were valid, and half a dozen were either blank or invalid. Thank you.
Thank you very much, Bill. I should ask you if you have any questions to me about the annual report, or to Bill, or to any of the other officers. Right, well, if not, we can move on to something possibly a little bit entertaining. Oh no, first of all, I've got to give some notices. I've got to tell you that the things coming up, our radio astronomy section is holding a Zoom session on 8th of November on binary stars and stellar cannibalism. If you want to take part in that, you contact the radio astronomy director, Paul Hearn. Then in November, Saturday the 30th of November, we have a Back to Basics meeting at the University of Greenwich. But there's no point in telling you about this because it's already sold out. So well done, Marie-Louise, for all the publicity for that. Then the radio astronomy section is holding another Zoom, this time on cosmic ray muon measurement on the 6th of December. Again, Paul Hearn is the person to contact about that if you want to hear it. And our next meeting here is the Christmas meeting at 14:30 on Saturday the 7th of December. And we will have the drinks reception afterwards. And you book for both of those on the BAA website, and it's free. But book quickly. Now, we've got some papers to mention to you. So I'll ask Jeremy Shears to read out the papers that have been accepted by today's council meeting.
Thank you very much, Mr. President. There was a paper accepted at the September council meeting, which was the Opposition of Jupiter 1960 by Richard McKim. And at today's meeting, 2 were accepted. The Star That Stopped, The Star of Bethlehem and the Comet of 5 BCE by Mark Matney, and Saturn during the 2010-2011 apparition, Part 1 by Mike Foulkes.
Thank you very much, Jeremy. Thank you for all your work over the last year as Papers Secretary. Now let me introduce Steve Cookson. Steve is the chair of Crawley Astronomical Society in Sussex, and he's, I think professionally he's a software person, but he's very interested in all aspects of astronomy, particularly theoretical aspects. He's even had a paper published recently in one of the publications of the RAS, I think this,
Yes,
the memoirs.
monthly notices.
Yeah, had a paper published about the gravitational interaction of binaries,
Yes.
and how it supports Newtonian physics, as you'd expect, really, but it doesn't support any alternative theories.
Yeah.
Anyway, that's not what he's here to talk about today. He's here to talk about this rabbit, strangely enough. So this talk is entitled Carbon Dioxide Levels, Global Warming and amateur astronomers, making a difference. This is Steve Cookson.
Hi.
This is a bit, you have to get used to the echo.
Yes. Thank you very much. Yes. Oh, goodness. Yes, it's a bit shocking, isn't it? It's rather a plot to stop me waving my arms around. We'll come to these in a minute. This is really about my blood pressure. So earlier on, I'm at a sort of age where I think some of you may be too, where you start to worry about your blood pressure and things like that. And I was wandering through Wikipedia, as one does, and I came across a graph on Wikipedia showing CO2 levels, ironically, since the year before I was born. My blood pressure sort of spiked for about 3 days. And I thought, oh goodness, I need to do something about my blood pressure and maybe also about humanity. So let me just see what the order is. Okay, so the graph I saw is that one there, but let's start with an introduction first. So, interestingly, large parts of the world's population don't see a man on the moon or a woman on the moon. They see a rabbit. It can be called the moon rabbit, or it can be called jade rabbit, and I guess it has other names in Chinese and other, mostly Asian countries, but also I think Mexico. More about that later. So the thing that I wasn't expecting was how controversial this subject was going to be. So I gave it a run for its money at our last Royal Astronomical Society meeting in September. It was scheduled for about 45 minutes, and it took an hour and 45 minutes, largely because of audience participation. And I'm very sorry that we probably won't be able to do that today. Suffice to say, there's a lot of uncertainty out there. So I have put a few more graphs at the front, just to try. We won't have time for all of the interaction. It was quite fun last time, and we were all very careful about our blood pressure, so no one shouted. But it was a very nice and friendly interaction, and I hope we all got a lot out of it. I'm going to try and summarize the parts of that as we go through this. So it's about global warming and where we are. It's about what we can do, and it's also about what we can do as astronomers to share information, which we do anyway. So many of the things I've been doing over the past year, I've been doing some spectroscopy with a friend in the United States, sharing information. But weather information is also something that we might like to share. If a storm is coming over East Kent, for instance, then we in West Sussex might like to know about it, because we'd like to know that it's half an hour away or something like that. So I think there are synergies that we can get, and we can also measure CO2, and we can talk about CO2 to our families and our friends and things like this. So let's just get some facts out of the way. The first thing, this is the graph that I saw. It's been measured in Mauna Loa Observatory since 1958, the year before I was born. And you can see that it's gone from slightly less than 320 to slightly over 420. And you can see that the Kyoto Protocol, which was, I think, 1997, and the Paris Accord in 2015 have made not one jot of difference. And it was that really that spiked my blood pressure. I hadn't done any further research at that point. I just thought, oh my God, we've got all these people flying out to wherever the last COP meeting was, wearing funny ties and arguing about things and denying that there's climate change and all sorts of other things. And yet, the reality is nothing has happened. And we have known about this. Did you know that? Would you have guessed? We have known about this since 1896. This Swedish dude, Svante Arrhenius, published his rather catchily titled On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground. And, I mean, you can go through the rather attractive graphs and tables and things. But suffice to say, we've known about carbon dioxide and global warming since 1896. And we've done not a lot about it. And how do we know? So, we have measured more recently and I'm not sure when that red bit starts. There are some things I'd like to draw to your attention, and I just want to say that they're not deliberate. So the fact that it's red, is quite alarming. The fact that it's sort of ice cool and comfortable here is not so alarming. So you've got to feel there's a little bit of trying to alarm your audience or get your audience worked up by choosing the color red. And that wasn't my intention. These have just been plucked off the internet, so it's not my graph at all. But I want to say someone has done that, and I am not trying to emotionally manipulate anybody. I'm just being frank about the colors and the sort of emotional influence these things might have. But you can see, nonetheless, red or not, it's quite a steep steep rise, especially since the 1950s. The reason that it's red is because they've used a different measurement technique, not because it's more alarming. Okay, so there's another similar graph over a similar period of time from 1850, and you can see actually that the change in land use has been a fairly common factor in CO2 rises, and going back for quite a distance before 1850. But fossil fuels and cement, so cement also is a large contributor, which I didn't know about this, but fossil fuels and cement are a large contributor to the growth, and that number on the left is measured in gigatons. So if you add up all the years, so if you add up the 5s and the 10s and the 15s and the 20s and the 25s and the 30s and the 35s, you get about 1 trillion gigatons of carbon dioxide in the atmosphere so far. And you can see that actually the only good thing that's happened in the last few years is COVID. So COVID has made quite a nice difference when I guess China closed down its oil-fired power stations and things like that. And the global financial crisis, which you probably call the global financial, benefit ball or something, because it was rather good for the environment. One of the arguments that people, that took up quite a lot of time in our September meeting was, but it's cyclical. It happens anyway. It goes up, it goes down, it goes up, it goes down. It happens. Yes, it does. Absolutely true, as you can see here. For the past 800,000 years, it has gone up and down. But the highest over the past 800,000 years has been 300 parts per million. And even that was a bit of a fluke. Mostly it's about 280. Again, it's relative. So the baseline here is 150. I'm not going to pretend it isn't. So it is, again, skewed to make it look more dramatic. But nonetheless, this was measured in 2018 at 407, which is 100 higher than the previous highest. It only took, so that looks like quite a dramatic fluctuation, but actually between 300 and 200, yeah, it was a dramatic fluctuation, but maybe not as dramatic as it looks there. Nonetheless, I don't believe it was a lot of fun for the cavemen and the cave swans and the cave monkeys and all of the other sort of creatures who lived around during the ice ages. It can't have been a fun transition. And the reality is that climate change isn't fun. It might be natural, but even when it's natural, climate changes cause floods, they cause freezing, and they're not a lot of fun for the people who have to live through them. So even these peaks here can't have been a lot of fun for the fluctuations for the people who live, the people and the animals who lived, and the people and the animals who lived through them. But it's going to be a lot less fun for us now, and it's also going to be less fun for us when it comes down. It's going to be less fun in both directions. Okay, quickly over this. The figure 1.5 degrees was the number that was set in the Paris Accord, and as you can see, last year we hit it. But actually, they've talked about the running figure. So the running average, as you can see, is still below 1.4. But the annual figure last year was more than 1.5. The last time CO2 was at the current levels was 20 million years ago, well before mankind existed. Mankind's only been pattering its feet around on the planet for about the past 1 million years. So it was 19 million years before baby humans were running around that we last had CO2 levels at this rate. And we've all seen the headlines. People dying, Australia catching on fire, all sorts of other stuff. What's going to happen next? So there are a number of things called representative concentration pathways. And these have been put together by, as you can see, the IPCC, the Intergovernmental Panel on Climate Change. And this would be a good outcome. This is what politicians want us to believe, maybe that one. Most consultants and most organizations who are investing are thinking of these two. And that means it's going to get a lot worse. If I look at the last, 400 million, half a billion years of CO2 concentrations. I don't know how they did these earlier ones. There must be estimates, mustn't they? It was about 16 to 20 million years ago. It's about there, 16 to 20 million years ago, that we had similar concentrations. It's just a long, long, long time ago. A lot of history has gone under the bridge, a lot of extinction events, a lot of difficulty. So I just don't know that we want to be on a planet that's doing this at the moment. And the icing on the cake is that the half-life of CO2 in the atmosphere is 120 years. So if we've got a trillion tons of carbon debt in our atmosphere, it's going to be there, or half of it is going to be there for another 60 years. So, what can we do? I have bought this fun thing on the left off eBay. Not that one. That's a rather nicer photo. Mine's looking a bit more battered than that one, but yes, I have bought that one because I wanted to measure weather anyway, and I thought that measuring CO2 was linked to measuring the weather. So I thought that would be quite nice, and I thought I could measure the weather, create a sort of global plot of CO2 and the weather, and I could exchange it with my colleagues. Mauna Loa Observatory. Mauna Loa Observatory has been measuring this since 1958, as we mentioned at the beginning, and it's quite nice that it's an observatory. People are saying, what are astronomers doing getting involved with CO2? Well, actually, we have been involved for a long time, and I think it's just part of our portfolio of activities that we do. So that was the first prototype. I've ordered a few bits off eBay and Amazon Prime, and put them together and measured the CO2 in my office. I was probably leaning over it and breathing on it at that stage, but that's what it looks like. Then I 3D printed a casing for it. Sadly, I forgot that heat rises, and so having a computer in the bottom and a sensor in the top meant that the computer was heating the sensor. So it probably was not the best design I could have come up with. So Mark III, no, I won't. So Mark III, which is this one, is square. It has a little wall here between it to stop the heat crossing over between them. So there's a CO2 sensor, there's a temperature sensor. Because you have to benchmark it, you have to adjust it for its temperature. And there's a little Raspberry, actually there is a little Raspberry Pi to do the calculations. And it creates a little web server. So it's a little mini web server that for my house will create graphs of CO2. So here we've got temperature, CO2, pressure, and humidity. And you can add other things. So if you've got a weather station like I have, you can either add rain or wind or whatever else you want to add to it. There it is on your phone, same thing on a phone. And I thought I would create a global map of CO2. Sadly, it only really has one. These are test measurements. It only has one. This global map at the moment only has one point, which is Crawley. I hope to build on that. We probably have 5 moon rabbits at the moment, distributed around 2 in the United States and 3 in England. And there it is again on a political. So there's a geological map and a political map. And there is the current moon rabbit. Okay, here's a version of it here. So this is a real one. Actually, it's given to me by one of my friends who's been using it. He wants me to download the data because he's got a bug on it that I need to fix. And really what I'm here to do is to call for collaboration. If there are people who are here who are interested, I am building a number of, I've got about 6 or 7 of these in the pipeline. If you would be interested, if you have an observatory, get in touch with me. I would be very interested in working with you. It's still a bit buggy. There are still some issues with it, but I think it's a nice idea, and you'll see some use cases in a second. So this is the sort of thing that, so you saw what I had, but this is what I'd like to have. This is windy. I'm sure many of you have seen the website. It's a very nice website showing the direction of the wind, sort of temperature and rain and stuff like that. I'd like to have a much more dynamic CO2 map extrapolated between observatories. So if we had 100 observatories measuring CO2, then I would extrapolate the concentrations. You'd be able to see factories that were emanating CO2, and clearly dealing with any CO2 emanations at source rather than later is a lot easier. It's a lot easier to say to a factory, burn less CO2 or cap your chimneys or something like that, than it is to then do carbon capture later in the day. Now here's an interesting use case. So when I started to do it, at the time we were living in a property on the South Circular, sorry, not on the South Circular, on the M25, and it had a green at the back. So there was a sort of woody green behind our garden, and I put the moon rabbit at the beginning on the back windowsill, outside the back windowsill, on the back of the house. And as you can see, I left it there for a day or so. And it's my son's bedroom. And my son came back. My son was at university, and he came back for the weekend. And so I had to move it to the front. So I moved it to the front of the house, and I put it on the front windowsill. And you can see at that point that it jumped, and it became a lot more volatile. So it's the volatility, I guess, maybe due to cars passing. And this one here, I think this is the bin lorry coming to pick up our bins, parking outside our door. And you can see it's very sensitive. I am quite surprised at how, I wasn't expecting this level of sensitivity, and I wasn't expecting the Amazon van to trigger it, for instance, the Amazon delivery van or the bin lorry. I wish, as I say there, I wish I'd had a webcam recording it. And I think actually, so the guy who lived next door to us at that point was also very interested. He saw what we were doing, mainly because we were rewilding our front lawn at the same time. And rewilding our front lawn really got the neighbors talking. But he was also very interested in the idea of measuring CO2. So I made one for him. And he has a camera on his front doorbell. And so he managed to rewind his front doorbell camera recording to look at the peaks. And he indeed was finding delivery lorries were creating peaks on his CO2 measurement. He put it in the roof of his house. So he put it next to the eaves in the roof of his house. There are plenty of other opportunities for using it. So the difference between, so I've got a teacher, friend of mine, who has got a student who wants to do a project comparing her uncle's living in London with her own living in Sussex. Gas central heating versus other forms of central heating, living near an industrial area, year-on-year change. That's going to be the hardest one because really it's not very micro-sensitive like the ones in Hawaii are. We can also, if we're doing astronomy and weather, we can track storms. That would be quite fun. I can see us having a project there. If we have several of these and we're capturing weather and passing weather across, tracking storms would be quite fun. And analysing the weather effects on astronomy, on seeing rather, and collaborate. Oh, that's another thing. Okay, moving on. But this is really the first step. So at the moment, I don't feel we all have access to the data. And one of the arguments in the meeting in September was about how can we believe any of this data? How do we know that it's real data? How do we know that it's not being curated just for us and for our consumption? And there's a certain, in the age of Trump, we have a sort of conspiracy theorist view of life now. And we have to accept that. And my answer to this is yes, absolutely. Measure it yourself. Build a moon rabbit. I've put the instructions on GitHub. Build a moon rabbit, 3D printed, a couple of Raspberry Pi components that you can buy off the internet. You have to calibrate it if you want accurate numbers, and measure it yourself. This is about democratizing data. So my feeling about this is, yes, all of this data is so hard to access. All of this data is made to sound so complex. But if we measure it ourselves and we see the bin lorry setting off our CO, you could put a little alarm on it. You could put a buzzer on it so that if it goes over a certain level, it sets it off. And if the bin lorry sets off your buzzer, then you write to the council, and it'd be quite a nice little project. You can imagine groups of people getting involved with it, with sort of this thing, and writing to the council together. So I think we want to bore everyone rigid with this subject. I think we want to collect this data ourselves. I think we want to tell our neighbours. I think we want to tell the people we work with. I think we want to tell our children. And we are doing it for our children and our grandchildren. Really. I am doing it. I don't want to leave I do not want to leave the planet in the state that it is to my children and to my grandchildren. And I don't think any of us do. However this ends up, I think there are going to be huge economic opportunities for the successful societies in this. But we have to recognize there's a problem. There's going to be a lot of money in it. There's going to be a lot of industry in it. It's going to be like a space race. My son said that. I said, we were sitting there and I was talking through the presentation. And he said, you're not getting over the excitement. He said, this is going to be like a new space race. And it is. He was right. We're going to need new technologies, and we can be at the front of that, and we want a cleaner Earth to be a better Earth. So it cost me about £125 to make one of these. Actually, it cost me more at the beginning. Now it costs me about £80 each, I guess. This bit here, so this is called calibration gas, and I bought it from a company called Shore City. I've only got one hand, I'm sorry. Otherwise, I would screw it together, and you just put that in like that, and you put the moon rabbit in a box so that it has a known concentration of, sorry, you can't see that at the back, so that it has a known concentration of CO2, and you calibrate it just like you would your telescope to get the right concentration. So this is 2,000 parts per million. Actually, you can get 500 parts per million, and the next one I get will be a 500 parts per million because it's closer to the sort of 400 that we're looking at today. They're quite expensive, and I guess I need some more ideas. It's still a project in development, and any help that I can get, and anybody who'd like to get involved, we're going to think of better ways of doing this and to make it more accurate, to bring the cost of calibration down. And that's it, really. How are we doing for time? Any questions?
Well, very, very, that's a very good summary of the whole subject. Thank you. Very, very clear. Yes, questions, Dr. John Rogers.
Yeah, thanks for bringing up calibration at the end. But I wondered, how can you be sure that the calibration is accurate enough to measure the very small variations that you expect the global CO2 to change by over just a few years?
It's not. We have to rely on statistics. Oh, sorry. It's not. We have to rely on statistics. The ones in Mauna Loa are plus or minus parts of a part per million. So they're like 0.1 or I can't remember what the numbers were. They're like 0.1 parts per million. The moon rabbit is measuring plus or minus 30 parts per million. there's absolutely no comparison. The amount per year that it's changing, I think it's about, from memory, it's about 7 or 8 parts per million per year. That's well inside the error of this. However, if you have 100 of it, you can then start to average out, and you get the averages, and you can see on each moon rabbit, or I hope you can see. I'm not saying you can see. I'm hoping that I've only been running this since about March. I'm hoping that we're going to be able to see the change on each one. And if we see a change on each one, averaged over the course of the year, you should see this climatic,
The annual cycle.
the annual cycle, yes, which is, actually it's the annual cycle, which is 9 parts per million, and it's the annual, it's the annual change, which is about 4 parts per million. So comparing the two, if we can see the seasonal cycle as the leaves fall off in the northern hemisphere, it will be a good test. And if we can see the leaves falling off in the northern hemisphere, then we might begin to believe that we're within the sort of region of accuracy that we need to be for measuring the annual increase.
Any other questions? Steve at the back.
Great talk, Stephen.
Thank you.
Probably a question, but at the start you mentioned the early work, Arrhenius, about the
Yes.
effect of CO2 heating of the atmosphere.
Yes.
There was actually a much earlier paper about it by Eunice Foote in 1856.
Oh, was there?
Yeah. You can download it on the web.
Yeah.
She did experimental work and she measured the heat rise from CO2 in the atmosphere.
Yes.
So,
So we can't pretend we didn't know about it.
No, we've had plenty of warning.
Yes. Oh, sorry, one thing I didn't make clear is that, of course, there is a lot of disinformation about this from the oil companies and the gas companies. And we got to the stage where the organizer of COP28 last year, or earlier this year, was forced to deny that he wasn't a climate denier. So there is a lot of misinformation, and we will meet that as we talk to people about this. So we just need to be clear in our minds that it's a real phenomenon and it is caused by mankind's activities, and the outcome is unlikely to be good for us.
Another question in the corner here.
Hi.
I've got a fairly loud voice. Is it possible to use the CO2 room monitors that we have at UCL and hack them as a CO2 sensor?
I don't know, but they'd have to be outside. The problem with the CO2 monitors is that I guess they're inside to measure the CO2 for learning purposes. As the CO2 levels go up inside my office, and a lot of this I had it in my office, and the CO2 levels would go up above 1,000. And you start to feel a bit flushed and you get headachy. You'd have to have these CO2 monitors on the outside, but I don't know how accurate they are. I imagine they're based on the same sort of sensors that I have here. If you had one in your observatory, that would be good. Maybe you could make a business case for it.
Anything else? Well, there's no other comments. I'll thank Stephen very much for a novel talk. We've never had a talk on this subject before, and that's great that he's got an actual project that we can do. And maybe write that up in the journal soon, and then with the instructions, and get our members making those, and maybe make a network of get a network of observers. Well, thank you very much again, Stephen. So my last act really as president is to give another presidential address. I've already given 2 presidential addresses. The first one was the history of the telescope, part 1. Last year I gave part 2. So what else could I do? I could talk about the telescopes of the future. So that is my presidential address this year. And I made it a nice pink colour for you. So I can't actually predict the future, obviously. So this is a bit of an open-ended talk, but I can talk about some things that are definitely planned at the moment, some things that are on the horizon, things that may or may not happen, and I can pose some questions. So here's some questions. Telescopes of the future. Will they be bigger? Will they be not bigger, but smaller and smarter? Will they all be in space? What about arrays of telescopes? Will completely different types of telescopes be invented? And how will what we do as amateurs be affected by these developments? And there you can see the famous James Webb Space Telescope, which had just been launched when I gave my last presidential address, and has now been working successfully for a year. This is a fascinating slide. I found this diagram on Wikipedia, and there's too much information in here to mention, but somebody has gone to the trouble of drawing diagrams of the apertures of every large telescope on the ground and in space that's going at the moment, and some projected ones as well. And so this is a fascinating comparison. And in the top left, you'll see that tiny blue dot, which probably nobody can see in the top left, is the Yerkes refractor, 40-inch refractor. On the right-hand side, you've got this huge green thing, and that is the projected array of the extremely large telescope, which will be built, is being built at the moment in Chile. And by the way, this is a basketball court by comparison, and that's a tennis ball court on the lower left. And then last year, I talked about the Gran Telescopio Canarias on La Palma. That's the biggest single mirror, but divided into segments, the biggest single mirror telescope in the world at the moment. But that's slightly disputable, because if you added the two mirrors of the Keck telescopes together, they come to a bigger equivalent mirror. Also, if you have the two monolithic mirrors of the Large Binocular Telescope together, they come to a bigger mirror as well, as do the four mirrors of the very large telescopes, so in Cerro Paranal and Chiri. So it depends on your definition of the size of the telescope, which is actually the biggest in the world at the moment. But you can see roughly what they're like, and you can see how much more vast the extremely large telescope at 39 meters diameter will be. But there's some bigger circles in this diagram as well. There's this huge grey circle here, and that was the projected overwhelmingly large telescope. And that will not be built, but that was a serious plan by ESA before they decided to scale it back to the extremely large telescope. Not very good names. I think they should have named these telescopes after famous astronomers, especially British astronomers, obviously, especially BAA members, but they haven't thought of that so far. And there's even bigger circles on this diagram. There's one towards the bottom edge, and that is the Arecibo Radio Telescope, 305-meter diameter dish, which collapsed a couple of years ago, but it was the biggest fixed radio dish. But there's an even bigger circle on the outside. That's 500 meters diameter, and that is the big Chinese dish. That is the large aperture spherical telescope, the FAST telescope in China, 500 meters diameter. That is the largest telescope of any type that's ever been built, and probably will remain so for quite a while. And then there's some other things on here which I will talk about a little bit. There is somewhere, yes, this is the Large Zenith Telescope, this pink one, and this is a different kind of thing entirely. This is a dish of Mercury, which sits horizontally and is rotated. And there's, in the top right, this is another projected one. This is called the 30-meter telescope, and this is projected by the Americans, and I think this will be essentially a northern hemisphere equivalent of the extremely large telescope in Chile, but I don't have time to talk about that one. But that looks to be a very similar design to the extremely large telescope. So you can see how much things have increased since the 19th century, the Yerkes telescope being the largest telescope in the world. Also, we've got the Hale telescope, that's the Hale telescope, and that's the Mount Wilson telescope, 100-inch, 200-inch there. And another thing that's coming online very soon, which I'll talk about, the Vera Rubin Observatory, that looks like that. That looks like this donut-shaped aperture. And why it is this donut-shaped aperture, I will explain in a minute. So first, the extremely large telescope, 39 meters aperture roughly, and it's being built, and it's got quite a long way, so this is really going to happen. That's the artist's impression of it. The first light is expected in 2028. It's a segmented primary mirror, and even the secondary mirror will be 4.2 meters diameter. So ESO arrived at this design, European Space Agency arrived at this design after deciding that the proposed 100-meter diameter, overwhelmingly large telescope would cost about £1 billion, and it would be too complex to build. So you have problems that fabrication technology and also road transportation limits the size of single mirrors that you can make and move around. It limits them to about 8 meters diameter per piece. So the design that they come up with for the extremely large telescope uses segments very similar to the ones used in the Gran Telescopio Canarias and also the Keck telescopes and other major new recent telescopes which use segmented hexagonal mirrors. There's the schematic diagram of it. You can see it's on an altazimuth mount, and the instruments are all mounted at the side. And it's a Naismith focus, so the light will come out of the horizontal axis, the altitude axis, into the mirrors. I talked about Naismith and his telescope. In the first of my History of the Telescope talks, he designed the Naismith system in the mid-19th century so that he could sit on a turntable and just look into the axis, the up and down tilting axis of the mounting. He didn't have to move at all. And so it's nice to see that's coming back. So it has a primary mirror consisting of 798 segments, each 1.3 meters across, and each of them is thickness of only 50 millimeters. And each segment has 3 position actuators, and the sensors measure the position of these of each of the segments relative to its neighbors, and they feed into the actuators and they adjust the shape of the mirror continuously to keep its shape fixed against the wind, against gravitational changes as it moves around, against temperature changes, etc. And they're going to recoat with aluminium 2 of the segments every day. So out of this 800 odd segments, you can just take a couple of out, recoat them every day, and that goes on, repainting the Forth Bridge, as it were. There's the secondary mirror. The secondary mirror is the largest convex mirror ever made. It is slightly flexible, and it's mounted on 32 points, so it can be slightly deformed as well. And here's the overall optical design. So you've got the primary mirror reflecting light back up to the secondary, reflects it back down to a tertiary mirror. The tertiary mirror, or M3, is also slightly deformable. It's concave. And they've got 3 curved mirrors, and that is calculated to reduce the aberrations over a wider field than would be possible with a 2-mirror system. And then the final 2 mirrors, which are called M4 and M5, that's M5, and Foulkes is there, so that's M5, and M4 is that one, yeah, that's M4. Those form an adaptive optic system. M4 is the largest deformable mirror ever made. That has 8,000 actuators. Its diameter is 2.4 meters, and that will adjust 1,000 times per second, and that's only 2 millimeters thick. So 2.4 meters wide, 2 millimeters thick, very deformable. Whereas M5 is a flat tip tilt mirror, and that makes the final batch of corrections to correct for seeing and refines the image essentially. So it's quite a complicated system, 5 mirrors. Making very good progress. This is the state of it at June 2024. So they've nearly built the dome now. The idea of it is that it should enable detailed studies of exoplanets, be able to directly image them, studying the first galaxies in the universe, supermassive black holes, and it should be able to detect molecules in protoplanetary disks around other stars. There are other giant telescopes under construction. This is the Giant Magellan Telescope, and this is a somewhat different system. It's not as big, but it's got bigger individual mirrors. This uses 7 of the largest mirrors, it uses the 7 largest mirrors ever made. And it's under construction at Las Campanas Observatory in the Atacama. And it's the work of a consortium of 14 universities, but they're mostly in the USA. And all these pictures of the Giant Magellan Telescope are renderings. They're artist impressions. Not much exists at the moment. They have cast the mirrors, however. So this is what it might look like. It's going to have 7 primary mirrors, each measuring 8.4 meter diameter. Each one will have a support system consisting of 200 actuators and sensors to control the position and shape of the mirror, to within a fraction of a micron, they claim. They started making these mirrors back in 2005, and the 7th one was only made this year. And the construction of the observatory has not yet begun, though they have flattened the mountaintop in preparation. It also has 7 secondary mirrors, and it's a Gregorian system. It's effectively 7 Gregorian telescopes. So the secondary mirrors are concave. They are each 1 meter wide and 2 millimeters thick, and they will be deformable 2,000 times per second. And the air gap between the mirror surface and the frame of the mirror is used to form a capacitive sensor to measure its alignment and to feed back to tell the mirror, tell the actuators how to adapt the mirror's surface to the incoming light. And each of these secondary mirrors is paired with only one of the primary mirrors. It receives the light from only one of the primary mirrors. So it's effectively 7 constituent telescopes, but they all focus on one instrument or one detector. And it will have a lot of instruments. It will have up to 10 instruments. It will have various spectrographs, and a large part of its stated mission is to measure the masses of Earth-like planets, Earth-like exoplanets, by measuring their radial velocities. And it will be able to search their atmospheres for the biosignatures. And the Giant Magellan Telescope will have the only high-resolution visible light spectrograph on any of the giant telescopes that are planned to become operational in the 2030s. This instrument they're calling the Large Earth Finder. So they want to find Earth-like planets. But it will also be able to measure elemental abundances in stars, and it will also be able to measure stellar radial velocities. A lot of the publicity that I saw for the Giant Magellan Telescope claims that when it is completed, it will be the largest telescope on Earth. But this is clearly untrue because it is well behind the schedule of the VLT, Very Large Telescope. It's more difficult to make it because it needs larger mirror segments. And that's taken a long time. So it will probably be finished in the 2030s, whereas the Very Large Telescope looks like being operational by 2030. So the Giant Magellan Telescope will never be the largest telescope in the world. So I think this is just Americans bigging their thing up in competition to the European offering. Another system, which is coming online very soon and will have a big impact on professional and possibly amateur astronomy as well, is the Vera C. Rubin Observatory. The Americans always love to put the middle initial in everything, don't they? The Vera C. Rubin. But that was previously known as the Large Synoptic Survey Telescope, and it's been planned for a very long time. Discussions started in the 1990s on that. And they've given it a new name, but they've also saying that it's going to conduct the legacy survey of space and time, rather a portentous phrase, which has obviously been chosen to get the same initials as LSST. So that's the legacy survey of space and time. Anyway, it is currently under construction. It's nearly finished. It's in Chile, the Atacama again, as all these telescopes are. And the primary mirror was installed on the 4th of October, so less than a month ago. It's going to have the aperture is 8.4 meters, but that's slightly misleading, as you'll see when you see the optical system. It will have a 3,200 megapixel camera. And obviously that generates an awful lot of data. So a lot of the work that's gone into this observatory has been going into how do they automate the data processing, how do they sift it and find the interesting events and then distribute those to other observatories. And it's going to start, if all goes well, in January 2025. So it's nearly there. It's going to operate an automated sequence capturing an area the size of 40 full moons with a 15-second exposure, and it will return to the same area of the sky every 3 nights. This data will be processed in real time, and they want to issue the alerts for the interesting events within 60 seconds of detecting the changes in the sky. So this is instant, real-time feedback of transients to detect the first movements of novae, supernovae, and moving asteroids, and the first detection of asteroids and comets. And this data is going to be instantly available both to professional and amateur astronomers worldwide. And this is a little video. It may even have some sound showing you how it's supposed to work. Let's go back, let's go back. Go back to that video. Now, play the video.
How does Rubin Observatory collect so much light and move so fast? We combined 2 different mirrors on a single surface to make Rubin's unique 8.4 meter mirror. Light hits the outer surface first, bounces up to a 3.4 meter secondary mirror, back down to the 5 meter inner surface, and then up to the camera. This mirror design gives Rubin enormous light collecting power, but also keeps it compact and nimble, so it can cover the whole visible sky in just a few nights.
So, compact and nimble, that's the idea of it. Will it work? I suspect it probably will have quite a lot of downtime. I can see a lot of potential for that going wrong. And so don't despair that amateurs will never discover a nova or a supernova or something like that ever again. I suspect there'll be times when it's not working, and those are the times when amateurs or other observatories will make the discovery. Nevertheless, it's a thing that we need to prepare for. But there is another approach to this whole thing. Rather than building a giant telescope, why not have a lot of little telescopes? This is one such thing. This has been operating for quite a time. This has been operating since 2004. This is called Super WASP, and WASP is Wide Angle Search for Planets, and it consists of an array of 8 CCD cameras with standard telephoto lenses, commercial lenses, and 4 of them on each mounting. It gives a field of 2 degrees square, and it continuously images the night sky, capturing 100,000 stars per image. It gathers 50 gigabytes of data per night, per observatory, and it's there to detect giant planets, giant exoplanets, and it's been very successful at that. And this project was led by Professor Don Polacco, and he spoke to our Winchester weekend meeting. He was the Alfred Curtis Memorial Lecturer, and his enthusiasm really is developing small telescope, cheap methods of doing these surveys, particularly if he can take commercially available components and just buy a lot of them up and build a system, build software that can analyze the data in real time. And so this has been proved to be a productive line. And the next one that's been built like this is also already exists. This has been operating since 2015. This is called the Next Generation Transit Survey. And whereas the Super WASP was looking for gas giants, the Next Generation Transit Survey, which is bigger telescopes, it's got 20-centimeter aperture telescopes. This can find smaller planets. And so that built on the success of the Super WASP. And in his talk to the Winchester Weekend, Don Polacco was describing his latest project, which only joined the BAA, which was good after his talk, so that's nice. So one of his drivers seemed to be, he was very pessimistic about the problem of satellite constellations. He thought that will never be solved, and we'll just have a sky full of moving objects in the future. And so we need systems to filter those out. So he's trying to design a system to work around that. There's no pictures of this project yet because it only received funding this year. So I'm just going on what he explained to the Winchester Weekend. And basically, he's using these Celestron telescopes. This is the commercially available telescope, the Celestron 11-inch RASA, or Rowe Ackermann Schmidt astrograph, which incidentally we had a review of in the journal a couple of years back, by written by one of our members. And he's got lots of them, and they're going to be fixed on a bit. They're all just screwed to a beam. There's no mountings involved here. They're just fixed. And each telescope is pointed at a slightly different patch of sky. And this array of telescopes will produce a stream of data covering the entire visible sky. And it uses CMOS detectors, similar to what you got in back of your camera, your DSLR, whatever. Cheap equipment, again, mass-produced equipment that you can buy up en masse. And the key to this is fast processing of the signals, correcting for sidereal motion, so that it drifts across the chip because there's no drive to the telescope. But the software is correcting for that and building up an image, knowing that everything is advancing along at sidereal rate. Then the non-sidereal motions, either from near-Earth objects or space debris, they will stand out in the data, and so there will be algorithms to extract those out. So this should be able to detect supernovae and the optical counterparts of black holes when they merge, and neutron stars. And the idea is to gather the data at the moment of collision. Very much as it was with the Vera Rubin telescope, but Don Polacco thinks his system will be even faster, and he claims it will really revolutionize astronomy, but he's not one to understate his case, I found. What about some completely different ideas? This is a thing that was thought up by Isaac Newton. Everything goes back to Isaac Newton, doesn't it? He thought of everything back in the 17th century. Newton thought of the idea of spinning a disk of mercury at a constant rate. It will create a perfect paraboloid. It's a telescope, but it can only look upwards. Obviously, it can only face the zenith. It cannot be tipped. But Newton couldn't build one because he couldn't control the rate of spin. But the first rotating mercury disk telescope was built as long ago as 1872. The one in the picture was built by the University of British Columbia in Vancouver, and it was used for imaging the transit of an object through the zenith. So the Earth's rotation moves the star across the sensor, and there is a latent image or an accumulating image on the sensor, which is moved electronically in step with the movement across the sensor. So it's all added together, and it's then read out at the edge of the sensor. So obviously this is quite limited, because you can only image objects very close to the zenith. But the advantage is it's very cheap. This mirror cost, well, the whole telescope cost just 1% of the cost of an equivalent glass mirror telescope. This was only a test of the concept, as the site for this was not particularly suitable for astronomy. But the University of British Columbia now plans to build an 8-meter liquid mirror telescope. And this has the acronym ALPACA, which stands for Advanced Liquid Mirror Probe for Astrophysics, Astrophysics, Cosmology, and Asteroids. So that's a good one, ALPACA. But they've got an idea for an even bigger one, which will be called LLAMA. And that will have if that happens, that will have 66 individual 6-meter mercury telescopes with a collecting power equal to a 55-meter single mirror. So that would be the largest telescope in the world, if that was ever built. That would have a bigger light grasp than the Very Large Telescope. Seems a long way off still. But this one actually has been built, and this is working now. This is in the Indian Himalayas. It's called the International Liquid Mirror Telescope. Has a 4-meter aperture. And the lessons that were learned from the one in Canada have been applied to this telescope. So this is made of mercury, but it's also got a thin layer of mylar, of aluminized plastic, on the top. And the mylar prevents waves in the mercury due to air currents. It rotates once in 4 seconds, and the mirror floats on a film of air 10 microns thick. And there's also a cushion of air round the edge to prevent the rotor from moving sideways. Now again, the telescope doesn't track, but the movement of the object across the detector is compensated electronically. And there's also a corrector lens to make the movement straight instead of a curve. Star trails are normally a curve, and there's a lens involved which turns that curve into a straight line, and then that helps the computer analyze it, apparently. So again, this is going to be a survey. This is a survey. It's working now, and it is searching for new transients and gravitational lensing events, creating a lot of data per night, which other telescopes will follow up. This is just the discovery instrument, and then bigger conventional telescopes will do spectroscopy on the objects that are detected. I'll move on to say something about radio astronomy. This is another mega project which you will have heard of, the Square Kilometre Array Observatory. In 2 continents, part of it's in Australia, part of it's in South Africa. And the Director General of this whole project is Philip Diamond, who will be known to some of you as he is the Treasurer of the Royal Astronomical Society. And the headquarters of this project is actually going to be at Jodrell Bank in Cheshire. This is touted as being, when it's finished, the world's largest scientific instrument, so even bigger than the Large Hadron Collider, although I'm not quite sure how you can compare such different things. Anyway, the SKA consists of 2 main parts. It's got an SKA low telescope in Australia, and an SKA mid telescope in Northern Cape Province, South Africa. And if you look at their website, you'll see a lot of stuff about how they're working with the indigenous peoples to respect their land and giving employment to the locals and respecting the beliefs of the indigenous people over their land. So that's what they've got to do. This is the part in Australia, which will consist of these things that look a bit like Christmas trees, silvery Christmas trees. This is an array of 131,000 small tree-like antennas, and these are covering frequencies of 50 megahertz to 350 megahertz. And they're dipole aerials, and they're grouped into stations. You can see they're in little islands, and I'll show you how these stations are distributed. And this is the other part here. This is the part in South Africa. This consists of dishes, and this is the mid-frequency array, and they will have 197 dishes. And this is actually a composite image because some of this already exists. The part on the right already exists, and it's called the Meerkat radio telescope, and the part on the left is being built, and that will add to it. And that will cover the frequencies of 0.35 gigahertz to 15 gigahertz. And each of these dishes is a Gregorian telescope. So it's got a concave reflector, and it's got another reflector, and then the detector sits in between them. So I talked about James Gregory in my first talk, a Scottish mathematician who invented the first reflecting telescope. So that's nice that his work is still relevant today. They're offset Gregorian telescopes. Construction of this whole thing should be complete by 2030, but that's only the first phase. And they plan a second phase. So the idea of this is that having a lot of dishes synthesizes a large aperture, and the principles behind this were first developed at Cambridge by Sir Martin Ryle in the 1960s. So you've got a baseline, and in this case, the baseline is 150 kilometers for the South African telescope. For the one in Australia, it's a bit less, it's 65 kilometers. So you're combining signals from all these dishes, and to do that, you need a very precise timing and synchronization system. You need to correct for the difference in arrival times of the signals and for other environmental factors which affect the transmission of the signals. So that's the reason this is much easier to do in radio is because the wavelengths are so much longer. You've got more time to make that correction. For optical wavelengths, infrared, it's much harder. Not impossible, but much harder. And this is how these dishes, well, they're not dishes in this case. In the low array, the dots represent the stations, so they represent these islands of dishes. And on the left, you've got the central core, and on the right, you've got the overall arrangement of them. Now you see this whole thing covers about 80 kilometers from left to right. And it's rather pleasingly looking like a bit like a spiral galaxy. They've got a dense core, which is apparently to provide sensitivity to extended regions of low brightness. And the three spiral arms provide a distribution of the baselines, so they get sensitivity over a wide range of angular scales. And this is the one for the South African one, that's the dishes, and you can see a similar idea. There's a dense concentration in the middle, and then this spiral pattern, and it's calculated on a logarithmic pattern. The distances are increasing as you go out in a logarithmic manner. But there's a long-term ambition to have a second stage square kilometer array, SKA2, to expand the number of dishes and put them in other African countries. And the scope of that is not fully defined, but it could increase the resolution by 20 times eventually. I haven't noted down what the resolution will be in the first stage. So, space telescopes, we all know and love the space telescopes that we've got, the Hubble Space Telescope and the James Webb So what's coming down the line? Well, there's quite a few of them. There's quite a few planned. Some of them are listed here. There's a European venture called Twinkle and Mauve. There's one from China, Chinese National Space Agency, one from NASA. There's quite a few. There's one from Russians. Roscosmos are going to launch a UV telescope into space called Spectre, and there's one from Japan called the Lightbird, which will be a millimeter radio telescope. I haven't got time to talk about all of these, just deal with some of them. Blue Sky Space. I talked to these people when I visited the European Planetary Science Congress a couple of years ago, and I mentioned to them, well, maybe BAA could hire some time on your telescope, because they are a private company, but they're funded by the EU, and they're putting some relatively small satellites into orbit. There's one which is called Twinkle, which is going to do IR spectroscopy, and there's a second one called Mauve, which is UV spectroscopy. It's being built by Airbus, and they hope to launch next year. There's the Twinkle, that's the infrared one, and that's 0.5 meter diameter. And it's going to do spectroscopy of objects in the solar system and outside the solar system. It's going to be in a sun-synchronous orbit, so it's always on the non-sun side of the Earth, because infrared detectors have to be kept cool, but it will have an active cooling technology as well. And this is the ultraviolet one, this is the Mauve, and this is tiny. This only weighs 25 kilograms, so you could bring it here in a briefcase or a rucksack, and it's 13 centimeter primary mirror. That's to do UV spectroscopy. Here's a much bigger one. This is a mock-up of the Chinese Optical Space Telescope. The name Zhunqian means tour of heaven in Chinese. And this will have a 2-meter primary mirror, so it'll be much smaller than James Webb Space Telescope, which is 6 meters. But this will have a bigger field of view. And it will have an unobstructed optical design. It's got an off-axis design, and it will have various instruments, including a survey camera and a spectrograph and a cool planet imaging coronagraph. So the coronagraph is a thing which obscures the star, blocks out the star, and you should be able to image planets very near the star. So they hope to do direct imaging of exoplanets that are only 0.3 arc seconds from the star. And this is scheduled for launch in 2026. This is one from NASA. This is rather similar design. This is 2.4 meter aperture, rather similar. And again, a wide field of view. This is going to have similar resolution to the Hubble Space Telescope, but over a much bigger field, a 0.3 degree square field. And it's got a coronagraphic instrument to do the exoplanets. And it's going to search for gravitational microlensing events, and it's going to test general relativity, that kind of thing, curvature of space-time. Moving on. Well, what about, instead of having them in space, which is obviously, they're only going to last a little bit of time in space, and then they're going to fall down again, and you can't maintain them for very long. What about putting telescopes on the moon? This has quite often been suggested. There's a gentleman called Jean-Pierre Meillard at the Paris Astrophysical Institute, and he suggested using these permanently shadowed craters, which are very cold, at the poles. He suggested placing an infrared telescope of 13 meters aperture inside one of these permanently shadowed craters. And that would be much bigger than James Webb Space Telescope, and you could make it colder as well. James Webb Space Telescope can detect long wavelengths up to 28 micrometers. No, that's wrong. James Webb detects up to 28 micrometers, but this potentially could get to 200 micrometers. So it could image in infrared the very cold universe. And those wavelengths penetrate the gas and dust in our galaxy and other parts of the universe much more effectively. So, and it could also detect molecules in exoplanets' atmosphere that only radiate at those long wavelengths, and that includes water. So that'd be really useful to detect water on exoplanets. And the suggestion is that this thing could be built by robots. This is another, and this is a bit of a more official idea, so a bit more of a chance of happening. This is the idea of putting a radio telescope on the moon, a fixed radio dish. And this is a proposal by NASA to build an ultra-long wavelength radio telescope on the far side of the moon. The advantage of that, obviously, it's all the radio emissions from the Earth are blocked out. It's got a quiet sky. And it could, if it's built to this size proposed, it could detect wavelengths greater than 10 meters or frequency below 30 megahertz. The largest radio telescope we've got on the Earth, the Chinese 500-meter FAST telescope, is not sensitive to wavelengths longer than 4.3 meters because Earth's ionosphere reflects those radiations back into space. So that this could detect the stuff that's reflected off the Earth's atmosphere. And again, it's proposed that this telescope on the moon could be built by robots. And in this diagram, there's things they're calling these dual axle rovers at the edge. And what that is the rovers are robotic vehicles that, there's two of them, they go in pairs, and each of them has got a single axle. I don't really understand this, but apparently they can dock and undock from one another, and one of them will stand on the edge of the crater, and the other one will take the wire and pull the wire out, and then it will abseil down the inside of the crater and out the other side, and it will stretch this wire over, and then it will go round and do it again, and they'll build up this mesh, this radio telescope mesh, in this crater in this way. Finally, I'll talk a bit about the amateur market. Some small telescopes. These are some of the smart telescopes our members are using at the moment. These are the Unistellar Equinox. That's 4-inch aperture. It's a Newtonian design. It's a reflector. It's Newtonian design, and quite a lot of our members have got that. Some of the other smart telescopes are refracting designs, and you can see the sizes of them there and the prices of them. So these are automatic telescopes that set themselves up and plate solve to a line on the sky. So there's very little setup involved. They do all this themselves, and they take repeated short exposures. They've got altazimuth mounts, but they can compensate for field rotation, and you can control them on your smartphone. And they're proving quite useful for citizen science projects and for real research, because the data can be centralized easily and delivered to a database in a consistent format, which professionals can or other amateurs could easily analyze. And there are more of these coming onto the market all the time. The one on the left was new in 2024, the C Star. A lot of our members have those. I don't know anybody who's got the one on the right, the Celestron Origin. This is going to be a 6-inch Rowe-Ackermann-Schmidt astrograph. And this has a lot of features which more serious amateurs would want. It will give you access to the raw, unprocessed data files to process how you want. It will allow interchangeable filters, and it will have an equatorial mount or an equatorial mode to the mount with a wedge. And it'll be possible to do, therefore, long exposures with it, really long, many minutes. So I wonder if this works well, I wonder how long it will be before professionals get hold of them and just buy up a lot of them and set them up and find that's a cheaper way to achieve their objectives than building giant telescopes. I wouldn't be surprised. And here's the very portable end of the market. These are new this year as well. The Dwarf 3, is 35 millimeter aperture. That's an altazimuth telescope which you fit on your own tripod, only 400 pounds, little refractor. And the one on the right doesn't have a detector. You fit your smartphone into that, into the Vionis Hestia, and it uses your smartphone as the camera. And you put it on a tripod. It doesn't track, but it takes short exposures. And it has a 30 millimeter objective. Very cheap, and it's a thing you can put in your pocket. So in this talk, I've gone from 39 millimeter telescope to a thing you can put in your pocket. So it's time for me to finish, really, and leave some time for the sky notes with some conclusions, which are not conclusions at all, it's just my opinions. I think the biggest telescopes are going to remain earthbound for the foreseeable future, and I think the size limit of what is technically, financially, and importantly, politically possible to argue for may have been reached with the VLT, since they couldn't get the ginormously expensive one off the ground. But it's clear that a number of telescopes of that size will exist in the 2030s to 40s. And it's clear that telescopes in space will remain much smaller, and they'll be only used for the wavelengths that are blocked by the atmosphere. The idea of telescopes on the moon, although it has many advantages, still seems very far off. It's like bases on the moon, really. For all my lifetime, bases on the moon are supposed to have been 10 years in the future. So I'm a skeptic in this kind of thing. I just don't see it. I just don't see us having the technological and political determination to build big things on the moon. So I think that's a long way off. But what we know for certain is that the speed of data processing computing technology is leading to revolution in using small, smart telescopes for both professionals and amateurs. And as you've seen, we may not need the tracking mounts in future. For many applications, we may not need all that mechanics and all that precision to track at sidereal rate. If you can correct for the motion across the detector anyway, you may not need to track. And it's clear that an awful lot of observational data will be coming down the line in the next few years from these big telescopes and from small ones. And the BAA should be organising its members to make use of that data. Many of our members don't actually want to own their own telescopes. They live in bad places. They're just not interested in fiddling about and getting cold at night and covered with dew. But they want to have some data and make their own discoveries, and we can be facilitating that. So thank you very much. That's my presidential address for this year, and that's the end of my presidency for 3 years. And I'll now hand over to Mike to give us some sky notes. Thank you.
Any questions, David?
Any questions? Well, we changed the computer. There's the HDMI connector is over here. So that's the one. Any questions? Yes, are there any questions? Yeah, one. I've only got time for one. Yes.
It's really just a kind of observation, you know. I love observing with small telescopes, which most people would laugh at, like 60 millimetres, 70 millimetre. I stay in a multi-storey, and most of my life I've never had a garden. I've got a community garden. If I want to use a big telescope, I've got the observatory one at the moment where I work at. But it's amazing, particularly in the Astronomical Society of Glasgow, these small robotic telescopes are breeding, you know, and I find it amazing that people are using 50 millimetre telescopes, you know, and there's now a 21 millimetre one coming out that's, and I've been using small telescopes for decades.
It's become too easy, and it's increasing the number of images that
it shows you what you can do with a small telescope. Yeah.
Yeah. And quite a high proportion of what we're getting in the BAA online gallery now has been taken with sea stars.
Yeah.
Right, Ken, very
this 39-meter telescope, it's looking for black holes. Are they grouped in the black holes? Are they grouped in certain areas? Or?
I don't think so. I think the idea is to detect the collisions of black holes, and I think that there may be an optical counterpart to the collision. The collision can be detected using gravitational waves, and there may be, I don't actually know the details, but there may be an optical signal that can be detected.
That's why you got...
I think that was the idea of that, because in general, you can't see black holes in general, but when they interact, or it may not be two black holes, it may be a star falling into a black hole. That might be a thing that can be detected.
Right, thank you, David. Can everybody hear me all right? An apology, I had a bit of a cold and cough last week, so I'll suddenly break down. Just bear with me. There's been a lot of interesting things in the sky over the last few weeks and months, and there's also some nice things coming up over the next couple of weeks as well. So we'll go through them fairly quickly. We've just passed the autumnal equinox. The nights are getting longer, which is great for people who observe night, not so good for solar observers. And of course, last weekend the clocks went back, which meant it gets darker, really. Not always good for people wanting to change the clocks. But of course, the main thing has been the comet C2023A3 Tsushinshan Atlas, and that's the last time I'm going to use that name. It's a bit of a mouthful. And of course, the press got hold of this quite a bit, all the various news outlets. Most of them sort of described it as the comet of the century, which, considering we're only 25% through this century, maybe it's still a nice comet. Often they said it dazzles observers. Well, certainly wasn't blinded by it. But one interesting thing was that one of my first personal observations was to see this comet through binoculars stood out really well with a full moon behind me, so very easy. But that well-known arbiter of science and journalism, the Daily Star, said that this is a once-in-a-lifetime comet, yes, and it was going to visit Britain. How it was getting here, I don't know. Was it by Ryanair or Eurostar? But there we go. But certainly it was a great comet, and if you're interested in something, it makes you excited, it might make you relax, make you happy. So our comet section director, Nick, was looking at a real cool dude here, out up on the Rock de los Muchachos Visitor Centre in La Palma. They're making with his equipment to observe the comet. And on that particular night, he produced this absolutely stunning image of this comet indeed, just with the twilight, nice tail, nice head, and an anti-tail as well. And Nick will correct me if I say this wrong, but I think that's caused by some of the comet particles, a little bit more massive, they're less affected by radiation pressure, go into the orbit, the comet's orbit, and when the comet's orbit is edge on, we see all this material. Is that correct, Nick?
Yeah, I mean, it's basically dust distributed around the orbit, and we're, on that particular day, we were passing through the plane of the orbit, so we saw it edge on.
Yeah, and interestingly enough, some of the pictures I'm going to show also show this anti-tail. Also at the visitor centre was Steve Knight. He took these nice two pictures. David has been talking about the Sea-Stars robotic telescopes, and this image was taken with a Sea-Star, and this one more conventionally, and shows the anti-tail again. And these Sea-Stars, I've taken a few images of the comet myself with a Sea-Star, and it really works very well. Now, I'm not only going to, there's so many images of the comet being taken on the BAA website. And I know Nick offered me money to have the whole Sky Notes on the comet. I won't do that. But I think it's just a random selection, not necessarily the best, not necessarily the worst. But this is, I think, another stunning one as well, taken by Paul Whitemarsh, with the comet in the twilight. This is one of the, several observers observed when it came from into the western sky around the 12th of October, and they've got this beautiful tail. And this is another one, much more wide-angle shot taken by Gary Gawthorpe in Rotherham. And again, you see this lovely tail. We've got some really good close-ups as well. This one by Peter Carson. And I don't know how long the tail was about that night, maybe 10 degrees, and still you can see the anti-tail. And this is another one taken on the same night by Grant Privet in Salisbury. And another, it's just a really nice comet. Not everybody observed by taking pictures. Some people observe visually. And this is a nice drawing by Richard McKim using two sets of binoculars, 10 by 50 and 20 by 50, and again showing this anti-tail. And this is another one taken by Nick Quinn. He was in Tenerife, and again showing this lovely tail and the anti-tail. But certainly many other observers observed it in twilight. Andrew Patterson. Though the comet was fading a little bit, we can still see the tail there. And, well, what can you say about this picture? It's a stunner, absolute stunner. This was taken by Martin Mobley, and his location was somewhere in the Utah deserts in the US, using a 106mm telescope, and you can see, again, part of the anti-tail and everything else. Absolutely stunning image. I think this made the BAA Picture of the Week. And just to finish off, we have to let Nick have the last word on the pictures. This was posted first thing this morning. Managed to pick it up before I came here. And now we've lost the anti-tail a little bit more out of the plane of the orbit, and it's stretching out there. This is an interesting plot. It's taken by David Boyd, and it's a spectrum of the comet. And it was taken with a C11. He used a LISA spectrograph, and he was able to see some lines in it. Dave's in the audience. Is Dave here? Yeah. Would you like to say a little bit more about what you saw here, Dave?
Well, what you can see in the spectrum is a processed version of the image underneath, which is corrected for atmospheric and instrument sensitivity, which makes it much brighter in the middle and fainter at the end. But when you correct for that, you get essentially a smooth spectrum right through the wavelength range, apart from a very big peak at the cyanogen line at 388 3 angstroms, and very few of the other lines that you normally see in a comet. You usually get a lot of diatomic carbon line, cyanogen, NH2 peaks. It's lacking those, and it appears from comments made by professionals earlier that it's a very carbon depleted comet, which is why you're just not seeing evidence of carbon molecules in the spectrum.
It's a very, very dusty comet, which is what that continuum is, isn't it?
Yeah.
And I mean, it's a comet in a very, very long orbital period as well. So you may have seen in the media people talking about 80,000 years. It's nothing like that. It's many, many hundred thousands of years. So this comet may have been around before, it may not. We don't know.
One interesting thing you can see, if you look below the sodium line at 5.8, just a bit to the right, that one. In the spectrum underneath, there's only a small line coming out from the bottom, not from the top. And we think that's probably because it's picking up sodium in the tail of the comet, which is obviously flowing to one side from the nucleus.
This is the plot of the brightness of the comet. I'd like to ask Nick again to comment on this, see how it's filmed, because this was just before it went down towards the sun. How's it doing now? How's its brightness?
So, I mean, the other thing about this comet is being incredibly well behaved. It's unlike most comets, which basically do what they want. This one has been very well behaved. That blue line there is the predicted light curve based on the observations since it was discovered back in January 2023. But the interesting thing that happened at perihelion was a thing called forward scattering. Because the geometry was just right, we saw the magnitude increase by 6 or 7 magnitudes over what that prediction was. That was predicted beforehand, and it looks like the comet followed that almost exactly. It's now following it almost exactly on the way back down again. So, yeah, just a very, very well-behaved comet.
This is the path of the comet over the next month or so. Its position in November, coming up through Ophiuchus, the tail of serpents, and it's heading towards Altair, so it shouldn't be too difficult to find if it remains bright. Now, the sun has been active over the last umpteen months. These are a couple of images taken relatively recently. This one is by Paul Brearley, and again, it's using one of these sea stars, which David was talking about. Nice sunspot group, and this was posted this morning showing this huge prominence. This was taken by Brendan Timon, and he's put on the size of this thing, it's a really huge prominence. So the sun is still very active. And yesterday on spaceweather.com, and I'm not sure if this is truly accurate, they said there was a lot of high-energy proton flux passing the Earth, and this has affected several spacecraft detectors. And on the SOHO spacecraft, you can see flashes on the images, which is probably interacting with some of these nuclear particles. But of course, an active sun sometimes means aurora. We had the big aurora last May, there was one in August, one in September. But on October the 10th, we had another spectacular aurora that was visible over the length of the country. I'm going to zigzag up the country a little bit. This one was taken by David Strange down in Devon, just using an iPhone, and you can see the colours there. This next one, it was taken in North Kent by Honor Wheeler. I imagine this is probably looking more towards London way, and again you can see the reds and the greens. Moving further up, we've got Tim Hamus. He took this picture near Oxford, and you see all these beautiful greens and reds in the aurora. And then this is a really nice panorama constructed by John Rogers in Cambridge. He's put these pictures together, and you can see the lower leg greens and the reds at the top. I don't know about anything else. When I observed this, I could easily see the reds, but I was probably to my eyes, couldn't easily see the greens in this. Moving further north, we've got Greenwich Stanley in Lincolnshire, showing again, I think this Vega there. And then further north, we've got this from North York, this beautiful set of curtains. I'm not sure what the town is over here, it didn't say. But I must confess, my two favourite pictures I've seen on the web are these two, both taken in Scotland, where the aurora's overhead and you get the sort of corona effect. This one taken by Jimmy Fraser, and then this one by Bill Ward. Isn't that an absolutely stunning picture? And as the sun is active, let's hope we get some more auroras over the coming months. These are the phases of the moons up to the next BAA meeting, and of course, full moon is the thing that we don't want when they roar around, or if we're looking for faint comets. And the moon is always an excellent object to look at, even with a small telescope. I know this picture taken by Mark Phillips was quite a few months ago now, which shows a lovely crater chain, Theophilus, Cyrillus, and Katharina. So the moon is always well worth having a look at. And in August, we had an occultation of Saturn by the moon. This is a picture taken by Martin Lewis in St Albans, and it highlights the brightness difference between Saturn and the moon. Certainly a number of images that have been posted, some people have taken an exposure for Saturn, then overlaid it on a picture with the moon to get them the same relative brightness. But this is an interesting one taken by Steve Knight with a C9 and a bit inch celestron, showing the moon re-emerging in this occultation at the dark limb. I think that's rather nice as well. This is part of the Mare Crisium, and obviously the scene wasn't fairly good there. This is the night sky in the middle of November, and it's dominated by the square of Pegasus. The summer triangle of Vigo, Deneb, and Altair is moving over to the west, and the constellations of Orion and Taurus are rising in the east. Now, those of you who saw the comet earlier in the month may have noticed Venus very low down. It's still visible. Mercury is actually at an elongation on the 16th of November by about 22 degrees, which sounds a lot. But because the ecliptic is almost parallel to the horizon, it's not a very favourable elongation at all. But with Venus in the west, we've also got Saturn and Neptune in the southwest, Jupiter, Uranus, which will be near the full moon on the 15th, Jupiter, which will dominate the skies over the coming months, and Mars. So it's possible over the next couple of months to see Venus and all the outer planets in one evening. Now, Venus is at greatest elongation in January on the 10th. It's not a favourable elongation. It still remains rather low. But some observers have been able to capture some images of the planet. This is a nice set of images taken by Peter Tickner, which shows some of the clouds in there. Also, Mars is now becoming more prominent. Its opposition is in January on the 16th, and it won't be a really close opposition. It'll only get up to about 14, 15 arc seconds across. And over the next month or so, its angular size will range from about 9.5 arc seconds up to about just over 12. But several observers have already been taking pictures of Mars. This one on the list was taken when the disk was only about just over 6 arc seconds across. And this was taken by Mattia Piccoli, if I pronounced the surname correctly. And a similar picture was taken at almost the same longitude by David Basie, and we can see the same markings. This is the Mare Cimmerium and Mare Sirenum, and Elysium here, and either Clodes or bit of the North Polar Cap. But over this last few weeks, there's been a few minor dust storms. And this nice image taken by Nick Haig in Southampton shows some of the minor dust storms near the Solis Larkis Mare Erythraeum region. Jupiter will dominate the skies over the coming months. It'll be opposition on December the 7th. And this is a real stunning picture taken of Jupiter by Ian Sharp using a C11 telescope. Shows the red spot, it shows the turbulence following the red spot. As normal, we get lots of bright plumes and projections from the north equatorial belt. But of interest, there's a lot of activity and disturbance on the northern edge of the south equatorial belt extending into the equatorial zone. And there's other activity occurring in the planet as well. And John Rogers, the director of the Jupiter section, said that the spot's velocity has changed very slightly as well. And there are another couple of images of Jupiter. On the left, we've got Peter Tickner, and on the right, Constantius Bias. And these were taken a few hours apart. So you can see on the same night, the rapid rotation of Jupiter in a couple of hours, and also again seeing this activity in the southern equatorial zone and these plumes and projections there as well. And this is another one by Chris Hooker, again showing the great red spot, and this was taken with a sort of 10-inch, 250mm aperture telescope. Saturn is already past opposition. It was on September the 8th. And this is a close-up picture of Saturn taken by Trevor Barry in Australia. And with apologies to Trevor, I've actually over-processed his original image to an inch of its life to show one particular feature, which is just there, and I don't know if you can see it on this side, a very small dark spot. This is the remnant vortex from the big storm that occurred in 2010, and it's getting really smaller now. In fact, in August, at the end of August, the Hubble Space Telescope imaged Saturn, and it only just picked this thing up, so maybe this be on its last legs. But if you've had a look at Saturn over the last couple of months, the most obvious thing is that the rings are appearing very narrow, and it's sometimes difficult to even see things like the Cassini division. And this is a diagram I put on the Saturn section website, which shows the ring inclination over the next year. If it's a positive value, the north face of the rings is tilted towards us. If it's a negative value, the south face of the rings is tilted towards us. The blue line shows the inclination relative to the sun, and the rings will be edge on to the sun on May the 6th next year. And as the ring angle has been decreasing, many observers have been noting that the brightness of the rings is started to decrease, particularly after opposition. This shows the ring inclination with respect to the Earth, and this oscillation is caused by the fact that the Earth's orbital plane is a little bit different to that of Saturn, the ring inclined by about just over 2 degrees. So we get this annual oscillation as the Earth moves above or below Saturn's plane. And the inclination to the Earth is increasing over the next few weeks, but will rapidly decrease, so it's edge on to the Earth in March the 23rd. In this period, the unilluminated portion of the rings will be towards the Earth. But as you can see, this occurs not long after solar conjunction, so the planet will be very, very low in the twilight, even by about May. But when the rings do come back into sunlight, it can be readily seen within a couple of days. Another thing to notice is that the ring angle will get very small again in about this time next year. So it'll be about 0.4 of a degree. So if you've never seen the rings really narrow, wait until next year and you'll see them about 0.4 of a degree tilted towards us. One thing about the narrow rings is that most of the larger satellites orbit in the plane of the rings. So when the rings are virtually edge on, we can see transits, occultations, eclipses like we see with the 4 largest satellites of Jupiter. And earlier this year, there were some transits of Saturn's largest satellite, Titan. And they were only visible in daylight hours from the UK, but were readily visible in the dark hours from the US. And this is a nice image taken on July 6th by Gregory Shantos, showing Titan, which always appears dark when it's in transit going across Saturn's disk. And here the rings were very narrow. As I mentioned earlier, you can hardly see the Cassini's division. However, although transits of Titan have not been visible from this country, its shadow transits will be visible over the next coming months. And details are on the Saturn section website, and certainly on November the 20th, December the 6th, and on the 22nd, there'll be a shadow transit of Titan, which should be visible in relatively small telescopes. This shows the one on a simulated appearance on December the 6th, mid-transit. So well worth looking out. They're not very common events. Other satellites have been seen in transit, but they're very, very small. And this is an interesting one, image taken by Jeff Lewis in Norfolk using a C-14 under very good conditions. And I don't know if you can see there, possibly over there, there's a shadow, and that corresponds to the position of satellite Mimas. And that's, to the best of my knowledge, this is the first time I've seen an image of the satellite of Mimas. This one is an image taken by Mike Hood in the States. He used a 200mm aperture refractor, and the white spot there is satellite Tethys in transit. And here's another great image by Italian observer Luigi Moroni. It's a composite, different exposures to get the satellites, the disk of Titan, and there's a dark spot there, you can see it there, which is the transit of the shadow of satellite Enceladus. So those with larger telescopes may be able to something like this. Uranus and Neptune are visible, can be seen with binoculars or a small telescope. Uranus is in opposition on November the 17th, and the full moon will be nearby. And Neptune has passed opposition, but many observers have been able to image features on the disk. This nice observation here by Konstantinos Bayas in Wiltshire shows the bright polar cap and the 5 largest, brightest satellites. And this image taken again by Luigi Moroni shows some vague markings on Neptune. They are vague, but there doesn't seem to be much happening on Neptune compared to what was in the 2016-2017 apparition. Now, normally you need large telescopes to detect the satellites of Uranus, but last year I found, using one of these sea stars, you could actually image 2 of the satellites of Uranus and the largest satellite of Neptune, Triton. And here we see similar things using a sea star by James Whiteman. And he's actually managed, this is enlargements of the image, managed to capture Titania and Oberon of Uranus and Triton of Neptune. Something you can do with just 50mm aperture. These smart telescopes are certainly, I think, quite good. We had the Perseids in August, and many images were taken of some very bright meteors. A nice one of Alex Platt, and there was also an aurora at the time. Another one by Peter Meadows, showing an image. And I think this is a really nice image. It's a time exposure showing the Milky Way. There's Altair, we've got Vulpecula up here, and a nice meteor there as well. We have some forthcoming meteor showers, but whether we can get images like that, I honestly don't know. We've got the Leonids with the maximum on the 17th, and you'll notice that there's a full moon on the 15th, so it'll make things difficult. And the Geminids now seem to be the more active meteor shower than the Perseids. They'll reach a maximum on December the 13th or 14th, and sadly, the full moon may be around, but maybe if you can hide the moon behind a building, you might be able to see some of the brighter meteors. Variable stars, lots of variable stars in the sky. The most famous, one of the most famous ones is Myra in Cetus the Whale, which will be readily visible now. And Jeremy's told me it's at its minimum, so it might start to brighten again. But for variable star observers, the big thing is, when is T Corona Borealis going to get brighter? It was supposed to be brightening up in September, nothing's happened. And again, this is an image taken by Duncan Hale, which shows T Corona Borealis is very faint. And at the council, after the council meeting earlier today, there were some jokes saying maybe we ought to open a book or a sweepstake of when this is actually going to go bang. So Jeremy, if you want to start the book now, it's entirely up to you. So hopefully this will go up very soon. Time is almost pressing, and there's so many fantastic deep sky objects in the sky. And this time of the year, we've got the Pleiades, the Orion Nebula will be coming up. But I thought I'd just show, to finish off, 3 images of images of three really well-known, easy-to-observe objects which can be seen with the naked, or two of them with the naked eye, or binoculars, or a small telescope. This is an image of the double cluster. I sees the object. It's taken by Diana Clark, and again using one of these sea stars, and it was on the night of the aurora as well, and nice object to see in any telescope. And to finish off, as our president is retiring now, he's finished, David, two images by David, I think we fit in. These were taken in Kellen Heath with a 66mm refractor. This is M31 and shown M32 and NGC 205. Great object in binoculars or a telescope. And the more elusive object is M33, the galaxy in Triangulum. And again, a nice picture. So, lots of things to see and do. Hopefully, over the next couple of weeks, up to the next meeting, the comet will still remain visible. We have, hopefully, we might get another aurora, I don't know. Lots of things to see with all the planets being in the sky almost at the same time. Look out for the transits of Titan's shadow. Hopefully you can enjoy this. If the cloud, if it doesn't, like the last few months, the cloud has always been, it's been cloudy. So hopefully over the next months we will get clear skies. And maybe for the variable star observers, they might get a Christmas present if T Corona Borealis goes bang. It's 8 o'clock. I've just finished on time, so thanks very much.
Thank you very much, Michael. Excellent summary of what's coming up. Thank you all very much, all of you, for attending. I'll just, in closing, tell you that we've had a few comments on the YouTube live stream. One of them came from a user called Calamity Guru, / Last Days, trying to give us some information about a comet on a Russian site, but they didn't succeed. And another person complained that I didn't compare any of the big telescopes with giraffes. So I'm going to go home and build a telescope the size of a giraffe. So thank you very much, Simon, for operating the live stream. And thanks, everybody, for coming. And we'll see you, hopefully, at the Christmas meeting, which is on the 8th, I think. No, 7th. Saturday the 7th at 14:30 here. Bye-bye.